Hello, everyone. In this topic, we are going to work on the role of statistics in engineering. As you know, in our course, we have 12 main chapters. So this is the first one. It's a part of like the books. If you want to look at the book while after watching this video, it's in the chapter 1, parts of the chapter 1 of the book. So it's like the from 1.1 to 1.6. Basically, this is the whole chapter 1 here that you can look at it. And if you, after looking at this video, if you have questions, please email me and we are going to set up a time and we're going to work through that. These are the topics that we're going to cover. So the first 5 chapters or topics is like basic statistics, and then we are going to learn a little more about the what's the point estimators, different point estimation methods that we have, like the intervals. It's like this, you made a guess here, so what like the first 5 topics is going to help us to know that, for example, if you want to find out mean, this is the way that you're going to find it. If you want to find out the variance of a population, this is the way that you would go with it. But after 5, chapter 5 is that, okay, so now how would you present it? Think about it. So these first 5 chapters is going to help us that I have a population. We had it we have it in the previous video, like the overview one. It's like that. We have the population. We are going to get a sample from our population to make a guess for our population. Think about it for a moment. I'm interested to know something about the whole people in Canada, all of them. I'm going to get a sample. I can't go and ask each of them. I'm going to get a sample after, like, let's say 1,000 people. Then get the data, make a guess from it, make some analysis, and find out my number from this sample. This number that you find is going to be like a guess for your population. You can't say you can't say 100% is valid for the population. So after chapter 5 here, like when we are talking about the intervals, the hypothesis test, for 1 sample, 2 samples. So here we are going to learn about that. How can we connect our findings from the sample for the population? How can we connect it to the population and make some conclusion for our population? And then after doing all of these ones, when our sample is okay, we can make a regression model out of it. So let's look at it. These are the lecture outlines. So the engineering method and statistical thinking, collecting engineering data, mechanistic and the empirical models, what's the difference between them, and then at the end, quickly, we're going to talk about the probability and probability models a little. These are the learning objectives. So we want to identify the role that the statistics can play in the engineering problem-solving process. We want to discuss how variability affects the data that we collect. We want to explain the difference between the enumerative and analytical analysis, discuss the advantage and designed experiments having comparison to other methods of collecting data. And we want to explain the difference between the mechanistic model and empirical models. You know both of these models. We just want to know the difference between them. We're going to clarify the difference between them. And then at the end, we want to discuss how probability models are used in the engineering and science. This from the previous lecture, which was the overview. At the beginning, we said that I said, okay, think about it. I'm interested to know that what's the percentage, like type of the phone that you have, and then what will be the percentage of the students like that they have iPhone or they have like Samsung or Pixel, LG, Motorola, all of these phones, different brands that we have. So through that one, we learned about 2 things. I said that the whole class is going to be my population. And I want to know that what's your connecting device, especially during this period that we are in. Everything is online. So one way is that I can call all of you. It's going to take lots of time. The other way is that I'm going to make a sample and call a few of you, like a sample of that one. So let's have a definition. We are going to work with these with these two definitions a lot in our course. So the population is a collection of all measurements of interest to the statistical analysis, maybe of infinite size. The sample is a subset of the data extracted from the population. So it's like and usually it's a randomly that we would get. It should be unbiased and randomly. So this is subset of the type of the phones students they have in the class. So these are the introduction of this chapter. We already talked about the population and sample, and two other things are the parameter and statistics. So the parameter is a characteristic of the population. A statistic is the characteristic of the sample. Let's see, what does it mean? So if I find out the average GPA of all the engineering students in Canada, let's say second year students in Canada, if I'm interested to find out that one, the GPA, the average GPA of all of them, it's going to be the parameter. But the thing is that if you want to do that, it's going to take lots of time, lots of energy. What are we going to do? We are going to get a sample, and on that sample, I'm going to find out the average GPA of the students in that sample. Maybe there are 2,000 students in my sample instead of having like 100,000 students. So among those 2,000, I'm going to find out the GPA of those samples. So we call this one a statistic. So when we are talking about the statistics, it's the data that we get from the samples. You might have this question that, okay, does it happen that sample and the populations, they're the same? Yes, it happens. If the population size is small, then we can have our sample. These are exceptions, right? So we're going to work on these ones during the course. So with the statistics that we said that the statistics is for the sample, right? So we have two types of the statistics, generally speaking. It's the descriptive statistics and the inferential statistics. Descriptive statistics is that, okay, everything that you have heard, like mean, variance, standard deviation, probably you have heard about these things, right? So all of these ones, like how to show the data, the bar charts, like histogram, it's written here in your like a slide, the pie charts, and these are the descriptive statistics. In fact, we say that the methods for organizing and summarizing for presenting data, that's, we call it descriptive statistics. Is that you are gonna, it is descriptive, right? This next one is the inferential statistics. Inferential statistics, it's in fact the methods for drawing conclusion about the characteristics of your population from a sample of the population. So it's like that, for example, when I want to, in the example of the GPA that I was telling you, GPA of the engineering students in Canada, so the sample that I have, the method that I would use to draw the conclusion on this GPA for the whole population from something in the sample, that would be inferential statistics. It's that you're doing something like inferential. That's inferential statistics. The next slide, these are some example of the research that we have right now in the like for a few years in the U.S. Department of the Energy. So for all of these ones, you can see that, for example, let's say the second bullet, low loss, high performance magnets will make motors more efficient. So this is the research that they are working. So what they can do for it, think about it. Try to figure it out. Pause the video here, and then after this question, of course, and try to think about it. What would the population here? What would be sample here? Because based on the population, you can think about the parameter, and based on sample, you can think about the statistic. And then you can think about what with the inferential, descriptive statistics and inferential statistics. Pause it, think about it, write down your answer somewhere, and then come back and listen to the rest of it. Okay, so we're talking about the second bullet point, right? So it's the low loss, high performance magnets will make motors more efficient. So what's going to happen here is that we need to have, we are interested to know that what's the effect of these magnets, right, on the motors, that they are like some specific types of the magnets, they're going to make the motors more efficient. So it's like that we need to find out all types of the motors that we have. That's our population. Let's say how many, like in US, how many, like maybe 200 millions. Um, it doesn't make sense to go and ask 200 million people to tell us that if we try these type of the magnets on their motors, what's going to happen, right? So we are going to get a sample out of it, out of these 200 million people. That's going to be our sample of the magnets that we have in our motor. And then here, what are we looking for? We want to know that low loss, high performance magnets, they will make motors more efficient. So we need to find out the efficiency of these motors based on the different low loss and high performance, right? So this is going to be our outcome that we're looking for. So we go to our sample. The sample, let's say I'm going to have 1,000 motors. Among these 1,000 motors, I'm going to get the data of their efficiency of the motors, the magnets specification. So these data is going to be my statistics. And then, and the thing that I do with this data, for example, I would get the standard deviation, variance, all of these things in these data points from the sample of these motors. It's going to be my descriptive statistics. When I want to make a conclusion, go back to the whole US, make a conclusion for the population, that's going to be my inferential, draw a conclusion, that's going to be my inferential statistics. You can try other bullet points for yourself and see with the same way of thinking. Practice it. That's a good exercise. So let's talk about data. When we say data, it's the raw measurements and facts that we use in analysis. Our data, they can be discrete or continuous data. It's very important that we would know that if our data that we are working with, is it discrete or continuous? Discrete is that you can count them, right? They're countable. It can go to infinity, but it can't go to the infinity. But it should be countable. That's the discrete one. And then we have the continuous one. Chapter 4 and 5, we have one whole chapter talking about the discrete statistics and distribution, and one chapter for the continuous one. Chapter 5 is for the continuous one. But now let's know a little about them, like different types of the data that we have, because when you know that what type of the data you're dealing with, you're going to choose the correct path after that, like the distribution that you're going to use. It's going to be based on this one. For example, is it discrete? It can be finite or countable, possible values. Continuous is the real value, possibly on a range. For example, the time range that we have, that's the continuous one. We have the other type of the data that we have is the quantitative versus the qualitative data. So with the quantitative, it's like that the quantity is important, right? It has the numeric value of it. For example, you go and buy 2 pounds of apple, right? So this 2 is the quantity here. So it has numerical value defined on a range. Order of value is meaningful. For example, height, age, weight, surface finish, rankings, the measurements, interval data, all of these ones. So when we say discrete data, they can be quantitative or qualitative. Continuous data, they can be quantitative or qualitative. These are different categories that we are talking right now. So qualitative data is like that. For example, super simple example. Let's say we are dealing with data at the university. And then we want to see these are the engineering students, these are the art students. And then we want to do some calculation in it. So how would you name them with the art and engineering students? So we call these ones qualitative data. It's like that we would assign a number to them. And here you can say that there are symbolic data, category data such as gender, the female, male, all of these ones, right? Degree program, as I said, the nominal numeric data. So it's like that, for example, we would say 1 is equal to the engineering, 2 is equal to the business, 3 is equal to the arts. So that's the way that we can work with it. Another thing that is important when we are working in statistics and experimental design is the knowing the concept behind the variation. So any change, differences, or uncertainty in a population, we call it variation. This variation cause some deviation from the real specification that we're looking for. For example, think about this cell phone that I have, right? So the lens of this cell phone, it should be a constant number, right? A fixed number. So let's say here, let's say it's 15 centimeters, something like that. So with this 15 centimeters, or a little more than 15, I'm just trying to count, like measure it with my hand. But let's say 15, 16 centimeters. So with this 15 centimeters, what I'm gonna do is like that when we wanna, and let's say I'm gonna generate this, like this is my product, the product of my company, of my factory. So after making this product, they're gonna measure this, right? So, and let's say I have 1 million of this one as a product in the company in the factory that I'm working. You can't go and measure. It's not feasible to measure 1 million of this product. So they're going to get the sample. For example, they're going to measure every 100 or every 500 products. They're going to just get it randomly. They're going to measure it. So this variation that I said, that 1 million was my population. So I'm going to get, let's say, 1,000 sample each day to measure it, to make sure that the specification, the length of this one is exactly the same as the specification in the catalog. So here, when you see it's written variation, it means that when I measure this, there would be a difference between my measurement and the specification. So when we say that it represents the uncertainty, right, in the population. So I'm going to get the sample, I'm going to measure it, so, and it's going to give me the variation. How can we show this variation? It's a variance. So when we are talking in reality, like in real world, and we say that, okay, so the variance is some number or standard deviation, we root square the variation, get the root square of the variance to have the to get the standard deviation. And a standard deviation has the same unit with the mean. That's the main reason that we would do that. But think about it, that this variance, in fact, it represents the deviation from the specification, from the what we are looking for. That's a variation that you see here. Another thing that is good that we mention here is that we have two equivalent perspectives when we are talking about the probability. One is the percentage of a population meeting some criteria. Another one is chance of any individual observation from the population meeting some criteria. So I want you to think about these two and try to find out the difference between them when you read it. Pause the video here, please. Think about it for like a few minutes. Again, write down your answer somewhere that you would remember it, and then come back and listen to the rest of it, like the answer that I'm going to say. So, with the example that we had with the cell phone, in the previous chapter, in the overview one. So we said that, for example, 40% of the class, they have iPhone. We get the sample, and then 40% of the class, they have. So we would say the probability for the iPhone is 40%, right? Now this, when I say probability, I can have two perspectives of it. One way that I can say, listen to this part, it's very interesting. One way is that I can say, in this second year BME students or CHS students, 40% of the students, they have iPhone, right? 40% of the students in the class was my population. I got the sample, found out the 40%. I'm going to say that, okay, so let's draw a conclusion for the whole population. We're going to talk about the margin of error, those ones later, but now let's focus on the meaning of the probability. So I can say 40% of the whole class, they have the iPhone. That's one way. Another way that I can say, which is very interesting, and it's very helpful for, it's good for the companies that they want to sell you cell phone. It's like that, to encourage you to buy a brand. They would use this trick. They would say, if you choose one student, one individual students, you don't care about the rest of the people in the world, what brand they have, brand of the phone they have, what type of phone. If you choose one student, that individual student, there's a 40% chance that he or she or it has iPhone. So it's like that. One perspective is that you're looking at the whole. You would say 40% of the people, they would do this, right? 40% of the people, they would buy iPhone. Another way is that you don't look at the whole. You would say, if I choose one person, the chance that that person, specific individual, has iPhone is 40%. So these are two ways. Both of them is a definition of the probability. It's coming from the same experiments when we want to get the data. So let's go to next part, and the engineering method and statistical thinking. We always say that engineers are, there are some ones that they are solving problems, right? We're problem solvers as engineers, especially when you're going to the industrial sector. You will see that, you will hear that a lot, that he's a good engineer, or that person is a good engineer and is a good problem solver. We have two types, when we are talking about the engineering problems. There are two types of the process or products. One is the, for example, you have your distillation column, and you want to refine your distillation column, right? In industrial application, we call it, I've been working in a refinery before. So when you want to, when something like this happened, it's like that you call it, you're doing the retrofitting, right? So it's the name, another name that we use for this refining existing products is retrofitting. You retrofit your process. You have your distillation column, right? Which generates, let's say, gasoline, and you have your products out of your distillation column. And what's going to happen is that you want to improve it with the experimental design. So you are going to do the retrofitting. You refine your existing product. The second one is different, is that you design new product or process. From the paper, you get the paper, you start designing your process. This second one, we call it grassrooting. Like if you went to your co-op interview and you have heard that, it's like the first one is the retrofitting, the second one is the grassrooting. With both of these, we are dealing with the statistics. Look at here, and this is the typical engineering model. We are going to develop a clear description, identify the important factor, propose or refine a model, and here, if we can, for defining a model, we can conduct experiments to get data and have our model. We want to manipulate the model, confirm the solution, conclusion, and recommendation, right? And sometimes we need to go back and do the iteration and do the for the after getting the like when we come for confirming the solution. So when you look at this engineering model, which part do you think that we can fit as statistics? So think about it a little, like for a few moments. We can pause the video, think about it, and then come back. So when we look at it, this part is the parts that we do the statistics, right? It's like that you identify the important factors, you get the data and do the analyze. So we said that we are gonna get the data, do the analyze as descriptive statistics, and with the inferential statistics, we are gonna draw a conclusion. So here is the part that we would do we would get the data. Okay. So the field of statistics deals with the collection, presentation, analysis, and use of data. All of the things that we do for this collecting and presenting is that because our main goal is that we want to make a decision, we want to solve a problem, or we want to design product or process. So all of these are we get the data to use in these for finding out these ones. So statistical techniques are useful for describing, understanding the variability. We talked about the variability a few minutes ago. By variability, we mean successive observation of a system or phenomena do not produce exactly the same result. So it's like that we are going to have a deviation from our specification. So it's like that there would be some variability. So when I'm looking at this phone, the lens, it should be 15 centimeters, the lens of this one here. But because of the different phenomena and like the observations that we have in our system and like noises that we could have, it's possible that it's going to be 15.01 or 15.02, right? 15 centimeters and let's say 0.1 millimeter. It can be, we can have these errors. So statistics gives us a framework for describing this variability that I said, and for learning about potential source of the variabilities. Because when we learn about the potential source of variability, we are going to see that which ones we can control it, which ones we cannot control it, and we would invest on the ones that we can change it, right? Here is that variability is encountered when a process is too complex to model and control completely due to this. For example, cost, time, resource constraint, incomplete knowledge of the process. All of these things, it can cause some variability. Look at here, it's written, could we build a desk with plus minus 1 nanometer accuracy? Now, let's say we are going to make it. We are going to spend lots of money and make it. Who's going to buy it? Why? There is no need for it, right? Generally speaking, for the market. Or, for example, incomplete knowledge of the process. That plus minus 1 nanometers, all it says here is that we have the variability. We have this plus minus 1 nanometers. But it's not important in this case. Or sometimes we have incomplete knowledge of the process. For example, atomic level interactions that we would have, or the inter and intra-level molecular interactions. So let's look at an engineering example. Here it says that an engineer is designing a nylon connector to be used in an automotive engine application. The engineer is considering establishing the design specification and wall thickness, some numbers. And then it's going to find out the pull-off force for all of these sample. So what do we have is that we have 8 prototype units that they are produced, and their pull-off forces measured like in pounds. So we have these 8 data. These are our data points, right? This is the sample. Our sample has 10 data points. So when with the dot diagram, what are we going to see is that, so we have this pull-off force here, and then you see the dot diagram here. It's very useful plot for displaying a small body of the data, let's say 20 observations. So when we are working with the data that they are like, let's say in machine learning, it's like we're talking with the millions of data points. So definitely this one is not going to be our first choice. This plot allows us to see easily two features of the data, the location of them or the middle of it, for example, and the scatter or variability of that. And, because when we say that the middle is around here, so you can see that what would be the deviation from it. So the engineer considers an alternate design, and again, it's going to get 8 data points. So with the dot diagram, you can see here, you can see the difference. For example, you can see that one of them is a little shifted to the right, the other one is a little shifted to the left. So it can be used to compare two set of data. It's still, the data points, they should be a small amount of the data points. So for that engineering example, what are we going to do? We would say that a random variable of the x, we can model it as like some number like mu plus some epsilon. This epsilon here represent the variability, or variability, like the deviation. Let's say this is my expected value. That's this mu is the number, like for the pull of force. Let me go back to the previous slide. So I would say that for these ones, the field dots ones, so I would say my expectation is that the mean would be here, for example. All the deviations that I have from it, so I can say each of these x's, so these points are x. X is equal to the mu, which is my expectation, plus some epsilon, plus some number, which is my variability. We call this epsilon here as a random disturbance. There is another thing about the statistical inference, which is good that we talk about that here. It says that statistical inference is one type of the reason. Look at here, we have the physical law. From the physical law, we are going to get our product design, right? Like we're going to write down the law, and then you're going to get the design. You're going to design your products based on different physics law that we have, physical law that we have. Look at the statistical inference. See how is it? So in the statistical inference, it's very interesting. You get your sample, and you make a conclusion for your population, right? So this is when you look at it, there are two different types of the reasoning. So here you have your law, you are going to design your product. But here you are going to get your sample from the smaller one, you make a conclusion for the bigger one. So we call this one a statistical inference. So the way that you would make a conclusion, draw a conclusion for your population based on your sample, that's going to be your statistical inference. We have enumerative versus analytic study as well. So with the enumerative one, what's going to happen is that I have a class, like in your class, I'm going to ask you what type of phone do you have. You're going to tell me like the sample, and then I'm going to say if the population is the whole class, 40% they have iPhone. So it's like that, or they have like Samsung. So here I would say in the enumerative study, I made the conclusion for the population. In the analytic study, what's going to happen is that I have my sample, and I'm going to analyze it and make something for the future, right? Make a prediction for the future population. In that case, we are working with the analytic study. Okay. Another interesting thing that we are going to learn in this topic is the 3 different ways of the collecting data. We have retrospective study, observational study, and designed experiments. When we say retrospective study, is that whatever historical data that you have for making let's say, regression model or make a model, let's say for now model, we are going to learn the outcome of this course. One of the main objectives of this course is that we understand what is regression model. So we have like 3 months at least to learn it. But with the retrospective or historical data, you're going to have 10 years of the, let's say, electricity load demand in Ontario hourly, and then you're going to make a model that is going to work for 10 years. So this data that you get from 10 years ago, we call it retrospective study. Another one is observational study. Observational study is the one that, okay, you don't do anything. You just go and like, you would hire someone and you would, or by yourself, you're going to record the data. You don't change the experiment at all. You're going to collect the data, not from the past. Right now, I'm going to observe the study. I don't interfere at all. So I have a distillation column. I'm just going to record the temperature of each trace, let's say every 10 minutes. That's the observational study, right? The third one is the designed experiment. Designed experiment is very interesting. You're going to change your experiment a little, right? Play with it a little to find out the data points that you want to work with. So here is the like written part of the whatever I said in the last few minutes. It's a retrospective study. The engineer would use either all or a sample of the historical process data. Observational study, engineer observe the process or population, disturbing it as little as possible. We try not to disturb it because we just want to observe it. Design of experiments, engineer change the purpose, like it has a purposeful change in the controllable variables of its experiment. For example, I'm playing with the I'm recording the temperature. I'm going to change the pressure of my column to see the effect on the temperature, right? When I'm recording the data. That's designed experiments. It's different than the historical and the observational one. It's like the one thing that it's important to learn in design experiment is that to know that which variables that you're changing, it's important, right? For example, let's say in the example of the distillation column, I would change the pressure. I can add I can play with the type of the trace that I have. If it's a small scale distillation column, I can play with the boiler temperature, the temperature that is going to be provided to your distillation column. These are that, but choosing which one you want to change and how much change you can have. Like it's controllable variable, it's in your control. That's the designed experiment, and that's what if you want to do, you need to learn statistics first before going to this design experiments. For example, here look is the ethanol distillation column. So this is the distillation column, and then it's like that example that I told you about the distillation. You can imagine it with this one, that you can do the experimental design. Actually, it's a good exercise if you think this way, and then we can talk about it in the summary session. So if this is your distillation column, how can you define the retrospective, the observational, and design experiment data in this one? Which one? Just write it down for yourself. That how would you name it that this is the retrospective, or how would you name it that this is the design experiment? So here you can see the design experiment part of it. So I have these trays. So this is my distillation column. Okay, I have the boiler. I'm just gonna tell you quickly what's happening here. I have my feed inside my distillation column. So based on their different boiling points, I want to get some products. So what's going to happen is that my boiler is going to add heat to my distillation column. It's going to go up. I have a condenser. So based on what's the difference between the boiling points, so I can get and here is a decanter, like after the condenser. So I'm going to get my top products out of the distillation column, as well as getting the bottom products for the distillation column. So in this one, so here for the next slide, what I need you to get from this slide is that, so this is my distillation column. I have the condenser. I'm going to get my top product. Some of them is going to go back after this decanter. Some of them is going to go back to my distillation column that I would distill it again. And we call it reflux ratio. So the rate that I'm going to have this top products go back to have, let's say I want to generate methanol. So the methanol should have some purity, right? To reach that specific purity, I would return some of the products to the column to use the heat that I have in the column again. And then I have the bottom products. So in design experiments, let's see what's going to happen here. So I have the reboiler temperature, which is important because it generates heats, right? I have the condensate temperature, like on top. It's very important because it's gonna condense my, it's gonna give me the top products, in fact, right? And then I have the reflux rate. So with the design experiment, what we are gonna do, we say that we are gonna change the reboiler temperature or condenser. For example, these are representing something. For example, this one is, if it's -1, it's like 300. If it's +1, it's 400 degrees centigrade. Condenser temperature, if it's -1, it means it's like, let's say 20 degrees centigrade. If it's +1, it's going to be like 40 degrees centigrade. The reflux ratio like this as well. So we are going to assign numbers to these ones. What's important in the design experiment is the combination of them. So we have another course, experimental design, it's advanced course. In the chemical engineering department at Waterloo. And it's a very good course. It's talk about how can you combine these ones. We're going to work on this one in this course as well, but in that one is the advanced one. We call it factorial design as well. So we are going to choose the best combination among these ones, right? When you look at it, see, you can't find two rows that they have exactly the same combination. It's a different combination that we have here. So look at here, I have the reflux rate, reboil temperature. It's a three-dimensional, right? And the condensate temperature. We have something we call it factorial design of the distillation column. And then we are going to choose the best one. These are some examples that I want you to work on it by yourself. Because right now we know what's the retrospective, what is the observation, what's the design experiment. I would suggest that you would choose one of these products and think about the manufacturing process of it. And then when you think about the manufacturing process, think what type of the data gathering you would suggest. Right? Just as an activity by yourself, think about it. See that what's going to be the outcome of it. For example, if you're working with the consumer product manufacturing of the sunscreen, if you are interested in knowing something in the sunscreen, what type of the gathering data you would suggest. Long life batteries. It's a very good exercise. Try to do that, and then you can check your answers with me in the Q&A that we have, and we can talk about it. But that's just activity that you would do that at home. Okay. The next thing that we have is that we talked about the dot diagram, right? So with the dot diagram, it's a good thing. It shows the variation. It illustrates the variation, but it doesn't identify the problem over time. So for example, look at this one. Whenever data are collected over time, it's important to plot the data over time. Okay. Phenomena that might affect the system or process often become more visible in a time-oriented plot, and the concept of stability can be better judged. So look at it like this. For example, acid concentration. We have the even I've been teaching this course. I was telling you in the overview, like around 8, 10 times, something like that. But it still is interesting for me. If when I see data like this, I'm like this, okay, so what's the point of it? I have the acetone concentration, so what? So I have the acetone concentration, acetone concentration of the 84 and 94.6, let's say. What's the point of it? Well, how can it's funny when you look at it. So this one can be valuable if I have it over time. Because of that, we have sometimes when we are observing the process over time, we need to represent it over time as well. So here you can see that this one is good. When you look at it, you would say, wow, I can see the trend of the change of this concentration, right? We have many situations like this that it's important that you would have the observing process, that you would need to observe the process over time and present it in a way that you would have it, you would have the time in it. So we have a few more items that we want to talk about before ending today's topic. One is that the difference between mechanistic and empirical model. At the beginning of this lecture, I told you that you already know what is it. So the mechanistic model is all of the physics law that you had, right? Ohm law, for example. That's the mechanistic one. So we would say mechanistic model is built from our underlying knowledge of the basic physical mechanisms that relate several variables to it. PV equal to nRT. That's the mechanistic model. So all of the mathematical models that you get from the physical mechanism, we call it mechanistic. The next one, which we use statistics for it, is the empirical model. It's very important. So empirical model, we use it in engineering a lot. So all of these data analyst jobs that you would see, they're looking for someone who would make a good empirical model. The other name that I can use when we are working in statistics, I can name it as regression models. So empirical model is built from our engineering and scientific knowledge of the phenomenon, but is not directly developed from our theoretical or first principle understanding of the underlying mechanism. So what would we do with the empirical model? We are going to get the data that I said that we have 3 types of the data, right? After we got the data, we are going to make our model for it. We are going to relate the variables in our model. For example, in the distillation column example, we are going to connect the relation, we are going to find out the relation between the reflux ratio, reboiler temperature, and condensate temperature, right? So this is going to be my empirical model because I found this. If you find your model from the data points that you have, that's going to be your empirical model. Just jump. This is an example that we will see. For example, suppose we are interested in the number average molecular weight of a polymer. Now we know that Mn is related to the viscosity of the material. So we have some, you can pause and read the example here. I'm going to go to the main objective here. Look at this one. I know that I have a variable. It's a molecular weight, but let's say M. My variable with the symbol of M, it's a function of V, C, and T. One is viscosity, the amount of the catalyst, and the temperature. So with the empirical model, I'm going to develop something like this. Look at this beta 0, beta 1, beta 2, beta 3. These are my parameters that I'm going to add it to this. It's just the coefficients, some constants. So in statistics, based on the data points that we get, we are going to find out these beta 0, beta 1, beta 2. It's interesting, right? So it's like that I would have the data points, and I'm going to find out these unknown parameters. That's going to be my empirical model. Based on data points, I'm going to find out these ones. Look at this. For example, this is an example. I have the observation number, like I have 25 data points. The Poole range, wire length, die height. So I have y, x1, and x2. So here my y is related, is a function of the x1 and x2. It's like that you would say y is equal to beta 0 plus beta 1 x1 plus beta 2 x2. This is my empirical model. But when I want to find out this empirical model, in this course, we are going to learn it, that from these data points and doing the descriptive statistics, how can I make that model? How can I make that regression model? Because when you make that model, then you can go to the next step. Then you can say that, okay, so if my length is this and height is this, so the pool strength is going to be this. Then you can have something for the future. All of the weather forecasting that we have, these are empirical models. So what are they doing with the weather forecasting? They're just going to get the data points, right, over the years, and then they're going to make based on some variables, they're going to give you the temperature, like hourly temperature. So this is I'm looking this way because there's a window here and I'm looking outside. So the weather outside, when we want to make it, find out this weather, the temperature or humidity, all of these ones comes from the empirical models, like the regression models. The three-dimensional plot that I said, for example, let's go back to that one. I have the lens. Actually, I really like this slide. I love this slide. It's very interesting. Look at this. I have the viral lens. Whenever I talk about the regression model, students, they think about the line in their brain. They think that, okay, so I have for example, I have the time of the day, and then if the sun is coming, so I would know the temperature goes up and down. Even when I show it to you, it's like that. I have a line of the empirical models, but in reality, it's not like that. And for example, look at here. I have my pool strength here, the length and the height. So this is the outcome. This is x1 and x2. If you want to connect them together, what's going to be? Is it going to be like a line? It's three-dimensional. Having a line in three-dimensional, you're going to miss lots of points if you do that. So when we say we are going to make a model, is that I want to make a model, I want to make a line to cover all of the data points if it's two-dimensional. So what I'm going to show you here, it's okay that it's going to be a small because it's not that much important. So look at here. I have my data points like this. It's two-dimensional, right? So I want to make a line to cover all of this. So it's like that. I want to make a line like this and say this is my regression model. So, but it's two-dimensional. With two-dimensional is fine. So what about if it's three-dimensional like this? I have the pool strength, I have the viral length, and the height. Think about it. Pause it. Think about it. Have your answer, and then come back and listen to this, please. So here, I can't have a line for like regression line for it. I would have something like a plate. Look at this one. It's like a plate that is covering all of the data points. Now, think about this. What about if I have 4 dimensions? What's going to be the shape that I would have? 4 dimension is nothing. It's like that. You have 4 variables. You have a distillation column. You want to know the purity of the methanol out of it. Number of the trays, 1 variable. Reboiler temperature, 2nd variable, right? 1 is the purity of the methanol as my product. Then the number of the trays that I have in my distillation column, 2nd one. And then the reboiler temperature, condensate temperature. Now I have 4, even is more than this one. Reflux ratio, the 5th one. So it's like that. What about 5 dimensions? So that's the part that knowing the statistic is super helpful, because without even imagining that, you can have a model with like 20 variables. It's very interesting. You can have a model with 20 variables without any imagination, but it's going to work, right? So this model is going to work, but it doesn't have any in reality, you can't have it. You can have it, like if it's 3-dimensional like this, yeah, of course, be my guest, have this plate, that's fine. But what when you have 10? It still is gonna work. It still is gonna give you the answer, right? And it's empirical model. Like you get the data one. It's not a mechanistic model. It's empirical. It's like the data points that you get, and you do the stats analysis on it, and then it's gonna give you the answer. That's very interesting, right? So in this course, the main objective is that we want to see that, look at these ones. I can have 3 different plates for covering data points, right? So we want to choose the best one first together. We want to learn how to make these beautiful plates, like mathematically, the equation of them. And then we want to learn a way to choose the best of them. Like when I make a model, I would make the best one. For example, for this example, the best one is going to be 2.26 plus 2.74, x plus 0.0125, x1 and x2, right? These 2.26, 2.74, and this number, these parameters are the variables that are the parameters that we want to find it. These are our unknowns. In statistics, we are going to try this to find out this number, and this number. If I have like 6 variables, I'm going to find out it for the 6 of them, 6 unknown. So here we say that we call this one regression model. We talked about that. And the estimated regression model, you see this hat? I remember this for the rest of the course. I'm going to repeat it in the other lectures as well. So this hat represents the estimated, means that I have this model based on the sample. So whatever we find from the sample, we call it estimated value. So I have my estimated regression model. So it means that I have some deviation from the real regression model for the population. Okay, so the last thing that here I'm going to talk about is the probability models. We're going to talk about probability a lot later, just 1 or 2 slides. Because this is a topic 1, we are just overviewing whatever we have in statistics in more details, the role of statistics that we have. So here is about the probability model. Probability models, we talked about the probability, right? Remember this one, we said that one is that 40% of the class, they have the iPhone. Another way that you can say is that if you choose one student, there's a 40% chance that that specific individual, like a student, it has he or she or it has the iPhone, or they have iPhone. The probability models help quantify the risk involved in statistical inference. What was it? Inferential statistics, right? That is risk involving decisions made every day. So the conclusion that you draw, the probability model is going to help us with that. The probability provides the framework for the study and application of the statistics. So as I said, we are going to work on probability models a lot in this course. In most of the chapters, there are lots of the probability discussion that we are going to have together. So let's see what we learned so far. Role of statistics, how variability affects deviation from the mean, our expectation or specification of the catalog, enumerative and analytical studies, collecting engineering data, like the 3 way that we can collect data. Can you name it? Pause the video and try to name it, the 3 different data collecting methods. And then come back. I'm gonna continue because I will say that quickly. Okay, so we said that we have the retrospective, which is the historical data. Observational is that you don't touch anything, or if you touch it a little, you just step aside and record the data, observe the data. And the last one was the design experiments, means that you're going to play a little with the controllable variables purposely, and then you will see the effect on the result. Then next thing was that we learned was about the definition of the mechanistic models and the empirical one. Mechanistic models, they comes from the physics law, physically things that we have. Empirical models are the ones that we make it from the data points, like the regression models, like this line. when I make. In reality, the thing happened with this line is that I can't have the regression like this is one model, 2, 3, 4, 5, 6, 4, 5 data point. I wouldn't have something like this. Whether I'm gonna have something like this. So we are gonna learn about it, that we can have different options for our model, and we are gonna have it. The next topic is about the probability. We learned a little about, like we just had one slide about the probability model. Just have it as a bridge to our next lecture. So make sure that you're gonna look at the lecture number 2 video, the next video, which is for the chapter number, like second chapter, which is the probability one.